Thank you, Larry. Good morning, everyone. It's a pleasure to be part of this session honoring Michael. I have several things I could say about Mike, but due to the fact this is an ACI virtual convention, I probably shouldn't, so I'll focus on the topic. So one thing that is clear, and you'll hear throughout the day, is that for over 20 years, or plus that, depending on who he was working for, Michael's been involved with PCA research and education involving concrete durability. Many of these topics will be approached today, including, of course, his expertise in SCMs and ASR, but also DEF, sulfate resistance, and very important to PCA, the use of Portland Limestone Cements. So my plan is to highlight some of his more notable works conducted at the Portland Cement Association, and they have had great influence on the development of cement and concrete technology. I've been lucky to know Michael for over 20 years and learned plenty from him and other colleagues that I met along the way. We met in 2001 at an undergraduate faculty enhancement workshop in Boulder. PCA co-sponsored those workshops back in the day. And one of Michael's many talents that probably won't be highlighted enough today is his value as an educator, not only as a researcher. He's had a key role in PCA's workshops and courses, and for many years presented as part of the PCA Professors Workshop, which was put together to exchange teaching ideas and topics, of course, but also the mediums that you use to translate this material to our next generation. That workshop has since moved on to ACI, if you're interested in it. But yes, Mike was a part of it for many years. Also, back in the early 2000s, it is probably where we spent the most time working together, was due to a series of distance learning products that Mike came to us about and we put together over several years. And these included many topics, including fundamentals, cement, supplementary cementing materials, aggregates, admixtures. One was on mix design and one on hot and cold weather. They were fundamental topics, but also good length and quality within them at the time. And we still use the content within them to reference in other documents. And Mike has also assisted with many other technical documents for PCA, white papers and reports, and it has included reviews in our most recent update of PCA's design and control of concrete mixtures. So, but what I'd like to focus on is more than just his presentation skills. I think many of you, I hope many of you have had the luck to hear Mike present at an ACI conference in the past. He's been an instructor for many PCA courses as well, including our ternary blend program and other contract training programs for our member companies. His presentation style is one of a kind, and so is his sense of humor. But I would like to point something out that I think is just a bit unfair. He has this accent, and he just sounds smarter than most of us. So I do believe his intellect has been proven, but and I'll get into that in further work. But I've witnessed him not finish complete sentences and trail off mid-thought, and the audience did not even react. So I do think that accent does play a role in his success as well. As a professor at UNB, Michael actually supervised many research awardees of PCA Fellowships, and those include Donnie Burden in 2003, David Smith in 2004, Ian Kosh in 2005, Sean Heyman in 2008, and Ashley Hosek in 2011. And much of this work will be discussed today. So what I'm going to focus on this morning is reviewing some of the most notable work that Michael has made to PCA through research. And I'm going to try to follow a timeline, but due to the topics, including limestone cements and SCMs and sulfate research, including Thomasite attack and DEF, these subjects interrelate. And of course, as you continue research, new information is found. So due to the subjects tying together, I may jump around a bit, but I do want you to see the evolution of his research at PCA and the meaningfulness this had to our industry. So what I've done is I put the title of the research project on the slide and who the main researchers were. But another thing PCA does is we typically put these research reports out as either a serial number report or a research and design. So when you hear a topic as R&D serial number, that just helps you find it here at PCA. So be happy to share these slides after this program. We reference this research in much of our published documents. This is what our members need to get their information. And one of the first projects Michael worked on for PCA was a literature review revolving the use of limestone in Portland cements and the effect of thomsite on sulfate attack. And there was concern that levels of limestone higher than 15 to 35% may indicate more susceptibility to thomsite sulfate attack in cold temperatures and wet and aggressive environments. So and of course, this came about in England, and there was concern in the States for this as well. Throughout the literature search, they discovered that there were no cases of thomsite sulfate attack related to the use of limestone in Portland cement, which was something our members cared about, as well as this data supported the proposal to permit the use of 5% limestone in Portland cements, which then became the ASTM C150 change. So this was a very important beginning work. Another program that he worked on was the role of heat curing in concrete durability due to the effect of lithium salts and chloride ingress on the DEF. So this was one of his students' work, Stephen Ekulu. This investigation was conducted in 2 phases on heat curing up to 95 degrees Celsius, and it was found that lithium could suppress and control DEF. It also showed that externally applied chlorides have a pessimism effect on DEF, and this deviated from a commonly held view that chlorides can help mitigate sulfate attack in marine concrete, as an example. So there was a mechanism describing the pessimism effect in this report that was useful to us as DEF came about in the early 2000s. Of course, you're going to hear a lot on ASR testing throughout today. One of the works that he really pulled together a lot of information, and this is when this test became extremely popular, was the performance limits for evaluating SCMs when using the accelerated mortar bar test. This was originally developed for the purpose of identifying ASR aggregates, but it's been widely used for SCMs, and a modified version of AMBT was conducted and turned into ASTM C15-7 at the time of this report. It was a very important report to us, especially for the findings. Our members cared about making sure that the results and limits were fair to all materials for use in concrete. And it was concluded that the use of a 14-day expansion limit for this test agreed well with the performance of concrete and field construction at the time. And of course, you're hearing about field studies now that are giving some differing information. Combinations of the aggregates and SCMs that passed this limit had a low risk of damage. However, there had been controversy in our industry on testing ages. And so you may read up on this as you get it more into ASR about the 14-day testing limit versus 28 days. One thing that does happen in our industry is if we think one thing's bad, well, what happens if we make it longer? Is that worse? What this research showed is that extending the duration of the test for a length such as 28 days is overly conservative, and it results in estimates much higher levels of SCMs are needed to control the expansion than is what is actually required in concrete for ASR mitigation. And furthermore, the minimum level of SCMs required to control expansion during the 14-day limit was in good agreement with the amount of SCMs that are required. So we took this information, very important to us, and the PCA's Product Standards and Durability Subcommittee developed a white paper based on this research for communications with Department of Transportation entities and other specifying agencies. Moving on to some other topics that you may be aware of Michael working on. One of the first studies on rapid tests for transport properties of concrete was conducted in the mid-2000s at UNB with one of his students, David Smith. And this test program studied relationships between RCP and resistivity measurements. It's one of the first papers published. Now there are ASTM tests on this, but it was found that there's a good correlation between the rate of chlorides through the RCP and through conductivity tests. So this is a good start to getting more field data available versus laboratory data and correlating the two. Another test that was conducted is the durability of concrete for high levels of fly ash by Donnie Burton. This was in 2006 as well. Michael loves SCMs, as most of you know, and we all are pro using products to the right volume. And I think Jason summarized it perfectly. It can make good concrete better, but if you're using it in the wrong amounts, it can make bad concrete worse. So this research presented laboratory data on the effect of curing and carbonation and permeability rates of high volume fly ashes. And the data did indicate that high volume fly ash carbonates significantly faster than plain Portland cement concretes at the same water cementitious materials ratio. And it showed that the degree of moist curing is important, and it needs to be offset by specifying lower water cementitious materials ratios, extending moist curing period, and also increasing the depth of cover when concrete is used. So all of these things are rules for corrosion resistance in concrete, and they can become staples for code requirements for reinforced concrete structures. So this is very important work that as mentioned, SCMs are a wonderful thing, but using higher amounts isn't always going to get you what you need. And that is why we also turned this data and other significant work that Mike has done and research into a report on optimizing the use of high volumes of fly ash in concrete. And it relates to using low levels as well as very high volumes of fly ash in concrete, and provides guidance for the use of fly ash without compromising construction. So several case studies are also highlighted in this report, IS 548. And it's always nice to have these real work projects that have specific volumes that you can identify. And for instance, in our chapter on high performance concrete, there are several of these case studies are used. Another example for Michael, moving on from DEF and his other favorite subject of ASR, he did a lot of work on lithium, and Mike and Doug worked together at University of Toronto, and once he moved to University of New Brunswick. And this report was by his student Ikolu on the effectiveness of lithium in controlling both DEF and ASR in concrete. And it was examined in heat cured mortars that were up to 23 degrees Celsius, followed by steam curing at 95 degrees Celsius, and then stored into a lime water bath. The results showed that lithium salt is able to reduce the occurrence of deleterious expansion from DEF. It also showed that controlling ASR and cementitious environments could control one or both of those mechanisms, which we've known since back in the Stark days. But analyzing the leaching properties of the lithium and alkali levels of the mortars, it was found that you need a lot of lithium to get the job done. So this was an important report for us. And then going on to these higher temperature ranges, there was a report done in 2006 by several of the people that you're going to hear from today on the role of non-reactive aggregates. And so this is the study that Jason's talking about and continued throughout the project. And so since Jason just covered, I won't get into great detail except for to just summarize that it's really important that they noted that after initiating the test programs, they found two important observations: that the expansions in the 60 degrees Celsius version were considerably less than those at 38 degrees Celsius, which they wanted to know why at the time. And even further reduction in accelerating testing at one laboratory was found, and they wanted to be able to compare those results. So basically, they discovered that it's hotter in Texas than it is in Canada. But what they also wanted to know was if the reduction in expansion when increasing these temperatures could be explained, and if there was anything about the alkali leachings that changed an increase in sulfates or any changes in pore solutions from leaching. So it confirmed that the accelerated concrete prism test has drawbacks. It also showed that we need a good test, whether it's rapid or long-term. What's important is that we get materials that are used in concrete mixtures on a job site, that we get a test that can validate that those products are serviceable when using them for ASR. So this was one of the first reports that showed we still have lots of questions. And then moving on, another thing that came about around the same time in the late 2000s was this issue that airports were having with potassium acetate as a de-icer, and whether it was a physical, chemical, or combination of attack, it was also exacerbating ASR. So PCA did some more research through UNB as well as University of Austin, Texas, and this paper showed the report showed findings from the concrete pavement, showed microcracking, paste alteration, all sorts of things on chemical attack, but also showed absolutely that if you increase the threshold of potassium acetate in the system, you're going to increase the propensity for ASR attack. It showed that it would be very important to figure out how much SCM level could help suppress this reaction. And so there was further studies on that as well. And then moving on to one of PCA's very near and dear topics is Portland Limestone Cements. So a lot of this was literature review, but very important. And then I'll get to the research that Ashley worked on and Doug Hooten and Mike Thomas did as well. This literature review was one of the first because, as many know, there's plenty of limestone cement used in Europe successfully for many years. However, Canadians and Americans want it with their own materials to prove that it can work just as well. So this was a literature review to show what cements were being used and introducing a new class of cements that could be up to 15% limestone. We started in Canada, showing the work and then getting it approved in CSA A3000 with Michael and Michelle Nopkin's work at University of Toronto with Dr. Hooten. What they found was many things, but they also, and this is what's important, you have to admit what you don't know. And what they did is they outlined what is known, and then what are the gaps in the research and literature. The further study recommendations, including data on sulfate resistant, was needed. They did have concerns, as you know, on Thomasite attack at the time. And there were some other questions on sulfate resistance with certain blended cements. There was a need to evaluate the performance of limestones on ASR and de-icer scaling and chloride resistance as well, so just typical durability resistance. And then they wanted to know if it changed carbonation rates to use higher volumes of limestone cements, and then also check the influence on abrasion resistance. So those were the summary findings at that time. What that did was lead us into what research needed to be prioritized in the future. And then there were further literature reviews done in the United States as well that helped us get 15% limestone approved. It was approved in Canada first, and then they started the durability studies in Canada and got further work approved in the United States around that time. So that's in 2011. We have ASTM C595 type PL Portland Limestone Cements. And that also includes AASHTO M240. The environmental benefits were noted, but what's really important is that they had discussed the durability aspects as well. And so at that time, it was approved for use in every aspect except for sulfate resistant. They still had some unknowns on Thomasite and other concerns. So with that, there was some future work done in summarized in the serial number report 3285 on sulfate resistance testing of mortar bars and concrete at between 5 to 15% limestone. So this work showed that there are no concerns for sulfate resistance with appropriate levels of SCMs, and there's no influence of limestone on sulfate resistance. And this work includes work by Ashley Hosek with the PCA Fellowship. So what does this mean for PCA? A lot of things, and really work provided by Michael and others directly influenced the acceptance of Portland Limestone Cements in the United States. Many state DOTs have adopted the provisions for use of PLCs due to their expertise. There are 37 states that have it as an allowed acceptance in their specifications. They are allowed by ACI codes, including 318 and ACI 301 specification. The building codes of the International Concrete Codes Council allow it, and Federal Aviation Administration allows it, and this is all due to work like this. If you have any questions on Portland Limestone Cement, I encourage you to go to our website, greenercement.org, and be happy to answer any of those questions. But to summarize, that's a lot of different topics. Like I said, if it has to do with concrete durability, Michael probably had a role in it at some point. So I'm not sure if I can properly convey in this short period of time the breadth of influence that Michael has on the concrete industry, or his diversity of talent that he brought to the table as well, with working with his fellowship students as well as other industry colleagues, Benoit and Kevin and their students. But perhaps it can be summed up by his eclectic taste in music as one of his more interesting selections. Michael's a big fan of Tom Waits, if you didn't know that. And if you've ever listened to Tom Waits, it's like listening to a combination of Bob Dylan and the Cookie Monster if they made a love child. Tom beats to the beat of his own drum, and so does Michael. So I think that they really are two peas in a pod. And I actually listened to Tom Waits while I put together this talk this weekend. But in all seriousness, Michael provided PCA volumes of data to improve concrete durability. For that, we owe you a deep gratitude, and I'd like you to join me in thanking him for that and conclude this session.